Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, welcome again to the TV learning program. I'm teacher Pascal, and today I will be with senior 4 students learning chemistry. And today we will go on with unit number 5, the trends in the variation of physical properties in the periodic table. And the lesson we have today is the trends in the variation of metallic character, electrical conductivity, and melting and boiling points. We have discussed other properties like the variation of atomic radius, ionic radius, ionization energy, but today we will go on with these other 3 properties. So before we go deep in the content of today's lesson, I want you to be careful and we read together the objectives of our lesson. At the end of this lesson, you should be able to explain how metallic character varies in the periodic table. You should also, of course, be able to explain or define metallic character. Explain how electrical conductivity varies in the periodic table. What is electrical conductivity? And after explaining what it is, you should be able to explain how it varies in the periodic table, either across the period or down the group. And number 3, you should be able to explain how melting and boiling points vary in the periodic table. Now, let us start with property number 1, metallic character. What is metallic character? We know that in the periodic table we have metals and non-metals, of course with metalloids. But when we talk about metallic character, it is something slightly different. It shouldn't be confused with the metals and the non-metals. Why? Because metallic character, it shows how readily an element can lose an electron. So if the element is ready to lose the electrons very easily, then that element will be having a very high metallic character. But if the element has a low or small tendency of losing the electron, then it has a low metallic character. So from the metallic character, we can distinguish chemical elements into metals and non-metals. And as I said, it shouldn't be confused with how hard a metal is or how soft a metal is, because it doesn't concern the strength of elements. So the definition, metallic character of an element, can be defined as how readily an atom can lose an electron. Remember, how do we determine the ease by which an element will lose the electron? We can use the atomic radius or use the ionization energy. Do you remember how ionization energy varies across the period or down in a given group? Think about it. How does it change across the period, ionization energy? As we move across the period, ionization energy increases. And what does it mean in terms of the ease, how easy an element will lose the electron? If it is requiring a lot of energy to lose the electron, then the metallic character is decreasing, because that ease of losing is reducing. So as we move across the period, the atomic radius decreases, and then losing an electron will become hard, and consequently, metallic character will also decrease. And as you know, when we move from the left to the right, we move from metals to non-metals. Why? Because the metallic character is decreasing. It is becoming harder and harder to remove electrons from atoms. Now, what happens when we go down in a given group? When we move down in a given group, remember, the atomic radius, how does it change? Down in a group, atomic radius increases. And how will this increase in atomic radius affect the change in ionization energy? So the ionization energy decreases, showing that it is becoming easier to lose the electron. And that means that the metallic character increases as you move down in a given group. So metallic character increases. Metallic character increases as you move down the group because the tendency of losing the electrons increases too. So what we have on the slide here, as the atomic radius increases, this is down a group, losing an electron becomes easier, and consequently, metallic character increases too. So in short, metallic character can be defined as the readiness of an element to lose the electron. And we can define or explain that, describe how the metallic character varies in the periodic table based on the ionization energy. When ionization energy increases, it shows that it is very hard to remove the electron. It is very hard for the element to lose the electron. So metallic character decreases. And that is the reason why we said when moving from left to the right in the periodic table, we move from elements which are more metallic to the elements which have a low metallic character. So we move from metals to non-metals. And when we move in a group from the top to the bottom, we get elements which are more metallic. So metallic character increases as you go down the group. Why? Because it is becoming very easy to lose the electron. So in summary, about the metallic character, it's that. That is what you have to always remember. And the next property is melting and boiling points. What does melting mean? What does boiling mean? When you are melting a substance, you are transforming it from the solid state to the liquid state. Boiling a substance means that you are transforming it from the liquid state to the gaseous state. So what is needed there? For those changes to take place, what do we need? We need energy. We have to supply energy. The two processes, melting and boiling, they are endothermic processes. So we have to supply energy. And what is the use of that energy? In the solid state, particles are so closely packed together. And in the liquid state, particles are also more closely packed compared to the gaseous state. So when you're supplying energy, what you do is to weaken the forces, the attractive forces which hold particles together in the substance, in a given state. If you have the solid state, a substance in the solid state, and you want to melt it, you have to provide, to supply energy, the energy which will weaken the attraction forces holding particles together in the solid structure. And as the particles will be weakened, then they will move far from each other and we get a liquid. It is the same if you want to boil a substance. You have to supply energy so that the particles, the attractive forces in the particles can be weakened, and then particles get separated. Okay? So, melting or boiling a substance requires to weaken the attractive forces that hold particles together. And if we are saying that we need some energy to weaken those attractive forces, we have to consider the strength of those forces. The energy you have to supply will depend on the strength of those attractive forces, the intermolecular forces. So if the intermolecular forces are strong, then you have to supply a lot of energy to weaken them. But if the intermolecular forces are weak, you have to supply a small amount of energy to weaken those intermolecular forces. So, strong intermolecular forces or strong attractive forces mean that we have to supply a lot of energy. And for weak forces, we supply less energy. Less energy must be supplied compared to what happens when we have strong forces. Okay? So, let us see what it is being said here. In this, if these forces are stronger, more energy will be required to weaken them. And then the melting point or boiling point will be higher. So a substance which requires a lot of energy for its forces to be weakened will melt at a very high temperature. Okay? It makes sense. You have to supply energy and supply energy. If it starts melting, then you stop supplying energy. But if it resists, you supply more energy. And as you supply more energy, the temperature will keep on increasing. So substances which have stronger attractive forces, they will always melt or boil at a very high temperature because it requires a lot of energy to weaken their strong attractive forces. And these forces, of course, will depend on the nature of a substance. We know the chemical bonding and the intermolecular forces. So, if, for example, we consider metals, in the metals we don't have intermolecular forces. They are not molecules. But we have the metallic bonding. So, the attraction forces in those metals, they are very strong. But even if they are very strong, they are different compared to what? Compared to different types of metals. Let us take an example of sodium. Sodium, magnesium, and aluminum. Which of the three metals has a stronger or has stronger attractive forces, stronger metallic bonding? Do you remember the factors we consider when determining the strength of metallic bonding? Yes, you remember them. So we have the number of delocalized electrons. Number of delocalized electrons. As the number of delocalized electrons increases, we get a lot of particles to be in attraction, to generate those attractive forces. And here, for sodium, we have one delocalized electron, while for magnesium we have two, and aluminum we have three. So for aluminum, we have more delocalized electrons than either sodium or magnesium. And because of that, we will have strong electrostatic forces in aluminum compared to these two other metals. So if the metallic bonding is stronger, then the melting point will also be high, because we have to supply a lot of energy to do what? To weaken those strong electrostatic forces in aluminum. So as the metallic bonding becomes stronger in this order, even the melting and boiling point will increase in this order. So aluminum has the highest melting and boiling point compared to magnesium and sodium. So what happens when we move down in a group, in the group of metals? We will consider here sodium, potassium, rubidium, and here we can start with lithium. What will happen? What do you think will happen? Here we have to consider another factor, because the number of delocalized electrons is the same. They are in the same group, so they have the same number of delocalized electrons. So here we have to consider the size of the cation. We know that as the size of cation increases, the electrostatic forces become weaker. So as the electrostatic forces become weaker, what happens? You find the metals to become soft, softer and softer. And if they are soft, then their melting and boiling point will be low. So moving from lithium to sodium, metallic bonding becomes weaker. To potassium, it becomes weaker, and then the melting point decreases. Going down the group, the melting point and boiling point decrease. Now, what happens when we consider the other part of the nonmetals? The nonmetals, we can take the example of period number 3. Period number 3. You remember the elements we have in period number 3. We have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. How do you think the melting point will change, or boiling point? From sodium to aluminum, we said that it increases. And up to silicon, it also increases. But why does silicon have a very high melting temperature or boiling temperature? It's because of the giant structure. You remember the simple and giant structures? Yes, you do. So because of its very giant, its big structure, the giant structure, it has a lot of covalent bonds which are strong, and they will always require a big deal of energy to be weakened. So it has a very high melting temperature. So what happens when we go to this group? Here we have to consider the intermolecular forces, as I said. And the intermolecular forces, how do they vary with the size of a molecule? Do you remember how they vary? As the size increases, the van der Waals forces become stronger and stronger. As the size increases of the molecule, then we get stronger and stronger intermolecular forces, the van der Waals forces. And that is the reason why in this group of nonmetals, we have sulfur, which has the highest melting point, followed by phosphorus, by chlorine, and the last will be argon. Why is it like this? It's because sulfur has it has the biggest molecule. Its molecule has 8 atoms per molecule. Phosphorus has 4, chlorine has 2, and argon is monoatomic. So as the number of atoms per molecule increases, even the size of the molecule increases. And we know that as the size of a molecule increases, the intermolecular forces become stronger. And then it will require a lot of energy to melt or boil the substances. What happens when we move down in a group of nonmetals? Let's consider fluorine, chlorine, bromine, and iodine. We will always consider the intermolecular forces. They are molecules. How does the size vary as we move down the group? It increases. And as it increases, the intermolecular forces will become stronger. As you know, fluorine is a gas at room temperature and pressure. This one is also a gas. And bromine is a liquid, while this iodine is a solid. This is a simple demonstration of how the melting point or the boiling point increases as we move down the group, and showing how the intermolecular forces are becoming stronger in that group of the halogens. So here we have some examples. As the metallic bond becomes weaker, then the melting point decreases. We know that going down the group, lithium has the strongest metallic bonding, potassium has the weakest, and then the highest melting point, the lowest melting point. Aluminium has the highest melting point because of the strongest metallic bonding. And here we have some values, the values we can use to show the boiling and melting temperatures of these elements. Here we have the melting points only. You can see from sodium melting temperature is 97.8, magnesium 650, aluminium 660, and on silicon it is 1,410. When we go to phosphorus, it's 44.2, sulfur 119. You see what we have seen and explained there. And when you move down the group, the melting point of fluorine is negative 220, very low compared to that of chlorine, which is 101. So you can see that the melting temperature in nonmetals, it increases as you go down the group, but in the metals, it decreases as you go down the group. Now let us go to the third property, the electrical conductivity. What is electrical conductivity? How can we define electrical conductivity? The ability of an element to conduct electricity, the electric current. And as we know, we said that we have different parts in the periodic table. We have metals, which are in blue. We have metalloids and the nonmetals. So when we say electrical conductivity, of course, you should understand that nonmetals will not conduct, with the exception of graphite, of course. Why? Because to conduct electricity, particles or the substances need some delocalized electrons. In the solid state, they need delocalized electrons. So metals have delocalized electrons, and because of that, they will conduct electricity. But nonmetals do not conduct electricity because they have no delocalized electrons. As I said, we have an exception of graphite. And what happens when we compare the electrical conductivity of elements in the metals, for example? As I said, we need delocalized electrons. Here we have 1 electron, 2 electrons, and 3 electrons. What does it mean to you? It means that aluminium with more delocalized electrons will be the best conductor in the group. It makes sense. It will be the best conductor because it has more delocalized electrons. And if we go down in a group from sodium to potassium to rubidium, let us take an example. Here we have the example of group 2 elements. relative electrical conductivity, 0.250, 0.224, 0.218. You can see it is decreasing. Why is it decreasing? Remember, in a given group, we have same number of delocalized electrons. So because we have same number of delocalized electrons, now we have to consider what? The size of the cation. As the cation becomes bigger, it will block, because of that steric effect, it will block the free movement or reduce the free movement of electrons, the delocalized electrons, hence reducing the conductivity. So as we go down the group, the conductivity decreases. And of course, in groups containing metals and non-metals, the electrical conductivity will increase as we move from non-metals to metals. I think it is very clear and easy to understand. Now let us go through the homework and I explain what you have to do. Explain how the melting point varies across period 3 in the periodic table. Explain how the melting point varies across period 3 in the periodic table. You have to consider metals, the metalloid, and the non-metals. Explain how does electrical conductivity vary in the alkali metals, that is group number 1. We have given the example of group number 2. So how do you think it will be in the group of alkali metals, group number 1? And question number 3, explain why bromine has a higher boiling point than chlorine. And the last, and of course not the least, which one between magnesium and sodium has a higher electrical conductivity? And you explain your reasoning. You will try the exercise, I'm very sure, and you will make it. So let me thank you very much for your participation, your attention, and for always being there to follow the TV learning programs. See you next time.